do, give me a thumbs up if you see that we're live. It says we're preparing.
We're live. We're good.
If you see that we're live. And good evening, everybody. I'd like to welcome you to the Rittenhouse Astronomical Society, a very special night for us. This is our September event, and we are located in the Philadelphia area. Our main office is in Media, Pennsylvania, and normally we'd be meeting live at the Franklin Institute or a couple of the area planetariums, but we've been doing this as a Zoom session alternately. I'd like to thank you all, and what this really does is it gives us a little bit of a wider audience that we can actually look for. So what I'd like to do is I'd like to start off a little bit. We've been working on our website recently, and if you're not familiar with it, you should be seeing it right now. Give me a thumbs up if you guys see it. And we're doing a lot of work on this in our background, and there's some new things I wanted to engage you with a little bit. Right up here at the very top is our events button. And if you go to our events button, you'll actually see tonight's event. This is Dr. Paul Halpern here. But more importantly for us, because you're already here, you know about this, is our next event coming up. And I wanted to start off and say a little bit of a word about this. This is the Wyoming High Country Lodge excursion. This is the 5th year that we've gone out to High Country Lodge. And I was talked into our AstroCora group. I had asked a couple questions, and I'd asked our members, would they be interested in me taking some notes or sharing some pictures with one of these trips? And I suggested possibly doing a blog post. One of the members, Alan, had said to me, Ted, I don't do that blog junk, but you're pretty interesting. So if you decide to post it, I'll follow you. So enough said on that one. I thought, let's give this a try. So what I'm going to do is I'm going to start off here with a little bit of description. The High Country Lodge is where we actually do this. And this is the spot you can go to right here. I have a button for it. Go to this one and the blog posts start to come up. And the very first blog I already posted because, okay, I have to say this, it's come out many times and my members joke me about it. If I were to die on the drive out to Wyoming, it was time to fess up to something that I've done. I couldn't put it in the title, everybody. I was too embarrassed. But this first post should really be called How I Desecrated Medicine Wheel. Yes, your president desecrated a national historic site. I did it very innocently. But if you want to understand a little bit about how our national monuments come about, and let's just say some of the things that people are told versus the reality of what's really going on, click the button here and you can read more. And what I'll do is I'll post as I go out to Wyoming. And the first post is a bit of a long one because it's describing why are we going to Wyoming? Why is this the 5th year we've actually traveled back here? And what's this all about? So you can check that out also. So that's on our blog page. There's a couple different ways to get to this. I'll take us back to our main page. And I'm actually juggling a couple pieces here. Okay, so if you look up top, we just took you to the events section. That was right here. And you can go back to your main section here. This is all pretty new down here, our blogs section. If you go to the blog section, there's a couple neat things that have happened. We've set it up in a couple different streams, society blogs. This is one we eventually hope to open to anybody in our society. They can put a blog post here. Lou started us off with a really good piece here. So that's actually a nice one if you want to read that one. But if you also take a look about this underneath blogs, do something a little bit different. Let me do it this way. And the second one I have down here is our officers report. I know we haven't put out a newsletter in quite a long time, everybody, but what I decided to do was I'll let our officers talk directly with you. I put my first post up here, all about us coming back in September, and I called it Finding Our Way. What you've really got here is a document that kind of shows our transition to this new website, but also explains how we're trying to survive in COVID. Somebody's going to look back years from now and wonder, how did society actually get through all of that? And it actually kind of shows you some of the things that we've been doing. And then the third column right down there, astronomical excursions, that's where I'm going to start putting my posts. And I'll do one every couple of days. I'll do it on our way out to Wyoming. And what I'll be able to do is I'll be able to show you, as some members have asked, where do you stop at, Ted? Where do you camp at? How do you drive out and get all the telescope gear out there? So again, this is truly the story of how I desecrated medicine wheel. I'll just put that out there. That way the truth will be known if I don't make it back. And I started with a post last night that kind of scared me. I thought I'd share it with you. That way you don't have to read it. But I was on this thing right here. I decided to go down to Seaside Heights, and I was on the windmill. And that's about 170 feet tall. It spins around 70 miles an hour. And I asked the guy when I get on, when I pause at the top, let me stop for a little bit there, because I'd like to see if I can see the Bighorn Mountains. I'm going to Wyoming this week. And the guy looks at me and he looks up at the sky and he says, Ted, I think, or not Ted, he just says, I think the clouds from Ida might block your view because that's a hurricane coming in. And I kind of laughed because I was joking with them. You can't see Wyoming from the top of the Jersey Shore on that little ride. And instead, I just said to him, I think the curvature of the earth might get in the way. Well, needless to say, it's very interesting who we trust our lives with when you get on a ride like that. He had no comprehension that you couldn't see Wyoming from the Jersey Shore right there. So I see that our guest speaker is with us now. You can follow me along on the Wyoming trip if you'd like. We've been doing this every year, and I'll tell you the story there of how that all happens. And at the end of this, I'll give you a little bit more of an idea about what we can use this website for. Dr. Paul Halpern gave us a great teaser, and it happened last June. And for those of you who weren't here with us in June, look on our YouTube page. You should go back and watch that meeting, because it was almost like the perfect cliffhanger. He teased us about a new book he was putting out called Flash of Creation. And if you don't know, or if you weren't here for the last talk, one of the unique things about Dr. Halpern is he really gets excited and conveys a lot of information about the people behind the science. What drives these people? What personal idiosyncrasies? What did they get into with each other? And how did they go about debating these things? So it's with a lot of pride I get to say welcome to Dr. Halpern to our September event. And for our worldwide audience, we actually go from September till June. That's usually our main pieces. And Dr. Halpern, let me make sure I can make you a co-host so you can do this too. In fact, Renee, can you find that in the background? I think you can do it also. Yes, no, Denise, anybody out there? Tell me when you're a co-host, Dr. Halpern. I said, say hello so we know we can hear you.
Hello, can everybody hear me?
And let me make sure I can get you to be a co-host.
I'm trying, you know, I can't do it.
I was sharing my screen. Sorry about that. Okay, so I think we can do it now, and I think I can find him and do it.
It says,
I can't. Okay, good. I can.
You should be a co-host now, Dr. Halpern.
I'm seeing it.
Okay, great.
Okay, take it away.
Okay, so.
And while he's setting up, everybody, just so you know, Philadelphia area has tornadoes bouncing all across the area. We're all supposed to be hiding in our basements right now, but we're brave enough to do this. And you look a little wet. You just drove through the storm, didn't you, from outside?
Yeah. So I actually took the train. I really wanted to be in my office.
Okay.
Because, I have my books here. So let me see if I can get my books on screen.
Okay.
You see it in the corner?
Yes.
Flashes of Creation. Okay. It's just a much better setup acoustically in my office than at home. I have my dog barking, and you'll never guess what my dog's name is. Kepler the poodle.
Wow, Kepler.
So anyway, can everybody see my screen now?
Yes.
Yes.
Yes. Thank you.
Wonderful. So I'm going to talk about my new book, and thank you, Ted, for the kind introduction. It's always a pleasure speaking to the group. I look forward to speaking sometime in the planetarium again, perhaps for any upcoming books. But so hopefully we'll be live within the next months, I guess. I hope. Wishful thinking maybe. But anyway, so my book is called Flashes of Creation: George Gamow, Fred Hoyle, and the Great Big Bang Debate. So from time immemorial, a lot of people have been asking questions such as, did time have a beginning? If so, what happened at that beginning? What happened at that genesis? How did the stuff of the universe emerge? How large is the cosmos? will the universe someday perish or will it last forever? But if we go back a couple thousand years, we don't see scientists asking these questions. We see philosophers. We see religious thinkers. So we have some examples here in these statues. And the fact is, they couldn't really answer the question scientifically. They could only speculate. So for example, Pythagoras, the great Greek philosopher, speculated that all is number, that everything's made up of numerical combinations. So he predicted that there are 10 celestial objects, including Earth and a counter-Earth. He had no way of testing whether or not there's a counter-Earth that goes behind the Great Fire, as he put it. But that turns out to be false. There's no alternative Earth out there. But he said that just because he liked the number 10. Democritus talked about everything being cut up into small, tiny pieces, but couldn't really explain what they're made of. And then Aristotle famously said that there are 4 elements plus something called quintessence, which is empty space. But he couldn't really prove that either. Why would everything be made of earth, fire, air, and water? It doesn't really make sense. So until the early 20th century, there was no scientific way of answering the questions of how the universe came about, how old is it, does it have cycles? These were all speculated, but no scientific way of answering these questions. Now, in the early 20th century, there were multiple revolutions in science. So there was quantum theory, which started in around 1900 with Max Planck, and then continued by Einstein in 1905, and then finally by Niels Bohr. So we see a picture here of Einstein and Bohr walking together. There was special relativity, which pertains to high-speed objects, and general relativity, which pertains to high gravitational systems. So all of these helped shape modern cosmology. Plus, sort of the child of quantum physics and atomic physics was nuclear physics. So that helped us understand stars and the universe itself. So let's go back to 1915, which is an important year in history and also an important year in my book. So 1915 was the year that Albert Einstein published his famous work, Die Feldgleichungen der Gravitation, better known as his theory of general relativity, the equations describing how gravity works in the universe. So Albert Einstein spent a lot of time and a lot of energy developing the mathematics for this. And coincidentally, that year, one of our two protagonists from my book, Fred Hoyle, was born in the town of Bingley, which is a small town in Yorkshire, an unusual place for a renowned astronomer to be from, because in England there's kind of a class system, or at least at that time, and most people who were in the Royal Society were from Southern England, from places like Cambridge, Oxford, and so forth. But Hoyle was very proud of his Yorkshire heritage, and he came from a family of people who worked in the mill and worked in, in the woolen mills, in the wool industry, so clothing industry. But he also had poets in his family. I was lucky enough in writing my book to interview Hoyle's daughter, who reminded me that Hoyle had a great-grandfather who was a poet, a famous poet in the Yorkshire dialect. So he came from a very interesting background. Of course, at the age of 0, he wouldn't have known about general relativity, but he soon would find out. Now, one of the most succinct ways of describing general relativity, which is so important to modern cosmology, is an expression by the famous physicist John Wheeler, who some of you might remember from a previous book I wrote, The Quantum Labyrinth. I talked about John Wheeler. And he said that space tells matter how to move, and matter tells space how to curve. So if we look at this diagram, we have the sun, and the traditional idea in Newtonian physics is that the sun has an invisible thread pulling on each of the planets. Of course, there's no thread out there. It's more elegant to talk about the sun distorting something. So the question is, what does the sun distort? Well, the sun distorts space-time itself and creates this gravitational well in space-time. And then because of the well, all the planets in the solar system move in elliptical orbits around the well. So you can see that here, that the shortest distance around this well is an elliptical orbit. So a much more elegant way of describing how the solar system works. Now, Einstein, despite developing a theory that was dynamic, wanted the universe as a whole on the larger scale to match up with Newton's picture. So he thought, okay, well, maybe the universe in our vicinity is warped, which is why the planets move in ellipses. But if you go out to the entirety of space, that space itself should be pretty stable. And he imagined space initially to be something like a giant hypersphere, which is the analogy of a sphere, but in one higher dimension. It's kind of like if you imagine a sphere like the Earth, only imagine taking a box, if you can somehow imagine that, and curving the box into a spherical shape, but through a higher dimension. It's a little bit hard to picture, but that was the Einsteinian static universe. But when he did that, he tried to solve his equations mathematically, and he found that this hypersphere was unstable. If you just jostled it a little bit, it would either expand or contract. It wouldn't stay stable. So he decided to add a fudge factor, something called the cosmological constant term, which acts as a kind of anti-gravity, and that basically stabilizes the universe. So it's inelegant. It's kind of like if you took the Leaning Tower of Pisa and developed a steel scaffolding structure to hold it up. Well, suddenly the Leaning Tower of Pisa goes from being a beautiful Renaissance building to being rather ugly. Well, that's what happened to Einstein's masterpiece when he added the cosmological constant, because the cosmological constant didn't really make any sense from the point of view of the geometry of the theory or the matter side of the theory. Originally, his theory had to do with just geometry, space itself, and matter and energy, and there was nothing more, which was the original idea. Cosmological constant was just an ad hoc term that he added. So a couple years later, Alexander Friedman, who was a Russian meteorologist turned cosmologist, decided to have a crack at solving Einstein's theory. And for one version, he left out the cosmological constant, and he looked at not just the hypersphere, but also what's called a hyperplane and a hyperboloid. A hyperplane is like a box that instead of being curved around just keeps going in all directions. And a hyperboloid is kind of a generalization of a saddle-shaped, or sometimes known as a Pringles potato chip shape. So imagine a higher dimensional Pringles potato chip, if you can, and that's a hyperboloid. Well, Friedman tried those kinds of geometries, solved the equations, and found that you have three possibilities for Einstein's equations, and you get as a solution a universe that either expands and then starts to contract again, or expands forever, or expands forever and keeps slowing down and slowing down. So these are three possibilities, which are called the Friedman models of the universe. Einstein was very unhappy when Friedman sent him his paper and said, well, this is just mathematical nonsense. It has nothing to do with the real universe. Of course, we know the real universe is stable. And then Friedman was all apologetic and said, well, I just wanted to show all the possibilities in your theory, Professor Einstein. I wasn't trying to insult you. I was just trying to show all the mathematical possibilities. So Einstein said, okay, fair enough. It's just a mathematical paper. Well, it turned out that Friedman was more right than Einstein about the expanding universe. We'll see that in a few minutes. So if we can picture the Friedman models of the universe blows up a bit like a balloon. And imagine stars, or more accurately, galaxies. And Friedman's time, they didn't really know about the distant galaxies. They just knew about the Milky Way. But very soon thereafter, they discovered that there are many galaxies besides the Milky Way. And eventually they learned, of course, that there are billions and billions. But at that point, they only started identifying some nebulae, which turned out to be galaxies. And if we imagine these as dots in a balloon and we blow up the balloon, then you can see that the space itself is getting larger and larger. So that's how the Friedman models work. Now, ironically, Friedman was, as I show in my book, a meteorologist, and he was very interested in how balloons expand, weather balloons expand, and he taught meteorology and did experiments with weather balloons. Now, he happened to teach somebody named George Gamoff, who was the other protagonist of my book. George Gamoff was born in Odessa, which is now considered the Ukraine. So it's a different country from Russia today. But at that time, it was part of the Russian Empire. And when he was of age to go to university, he went to the University of Leningrad, which used to be called St. Petersburg and is now called St. Petersburg. But it was briefly called Leningrad, named after Vladimir Lenin, the first Soviet leader. So while he was studying in Leningrad, and this is a picture of the young George Gamoff, he took a course in general relativity with Friedman and became fascinated by these ideas and fascinated by the Friedman models. So that would eventually become his pursuit. But unfortunately, as fate would have it, Friedman went up one day in a hot air balloon to the upper atmosphere to take some measurements. It was very cold, and he caught the chills. And sometime later, perhaps because of that incident, he contracted typhoid, and he died at a young age, 1925. So Gamov could not work with Friedman as a PhD advisor. Gamov was still pursuing a PhD, so he had to switch to a more practical PhD in quantum physics, which also benefited him because he learned some quantum physics, which became very important for his career. Now, let's move ahead to 1929, when this fellow, American astronomer Edwin Hubble, used the Hooker telescope at Mount Wilson Observatory to observe what were called the nebulae, but by using Cepheid variable stars, which are blinking stars for those of you who don't know, he was able to ascertain both their relative brightness and the periodicity of the Cepheid stars told him the absolute brightness or luminosity. And then by comparing the two, he could determine their distance. And he showed that some of the Cepheid stars in galaxies such as Andromeda and others were far beyond the Milky Way. So he proved, actually a few years earlier, he proved that they were independent galaxies. And with this 1929 observation, he combined that data with Doppler shift data of these galaxies, and he showed that all the galaxies except for nearby galaxies such as Andromeda are moving away from us, away from our galaxy. And he charted the relative speeds, and we'll see that chart in a minute, but that shows that the universe is expanding. Although Hubble did not believe it was necessarily expansion, he was willing to entertain other hypotheses. So he considered all different theories for that, including an outdated hypothesis called the tire light hypothesis, which says that light, when it travels a long distance, loses energy. And we know that to be false now. Now, another fun fact about Hubble was that before he was an astronomer, he was a fantastic basketball player. He played on the winning team for University of Chicago. And then he later became a basketball coach at a school in Indiana before becoming an astronomer. And then he won a Rhodes Scholarship to Oxford. And his whole personality changed when he went to Oxford. He adopted English mannerisms. He started to smoke a pipe, wear a tweed jacket, and speak with kind of a clipped mid-Atlantic accent, a bit like Cary Grant. He's decided to sort of affect an upper-class English mannerism, even though he was born in the Midwest. Perhaps that helped with his astronomy, I don't know, but he certainly had a regal atmosphere about him. And here's the chart he plotted of galaxies. And you can draw a straight line, its velocity versus distance for various galaxies. And you see a scatter graph, but these seem to follow a straight line path, which means that the farther out you go, the faster the galaxies are going, which points to an expanding universe. And that matched up nicely with Friedman's hypothesis that the universe is expanding. It did not match Einstein's static hypothesis. So Einstein changed his mind. It also matched the hypothesis of a Belgian priest and astronomer named George Lemaitre. George Lemaitre was a cosmologist and a priest. He kept those two professions completely separate, but he proposed in 1927 that the universe is expanding, basically replicating what Friedman had developed. And then after Hubble released his data, Lemaitre was all excited, and he proposed the idea of a primeval atom, that the universe expanded from a very, very tiny point in a burst, and all the matter was created at the beginning in something called a primeval atom. And Einstein was very interested in that idea, and they actually worked together on some models of the universe. So there's the two of them together, Father Lemaitre and Professor Albert Einstein. So here's Lemaitre's work on the primeval atom. And he emphasized that it had nothing to do with biblical Genesis, that you need to keep religion and science separate. Now, not everyone listened to him, as we'll see. Eventually, one of the popes, Pope Pius, got all excited about this idea and thought, well, this is a confirmation of biblical Genesis. But Lemaitre always said, keep science and religion separate. Now let's return to George Gamoff. So George Gamoff got a fellowship where he could go to Göttingen, Germany, which was a home of quantum physics and the home of higher mathematics. There was a lot going on there. So he worked with Max Born, a famous quantum physicist. And Max Born, as some of you might know, was also the grandfather of the singer Olivia Newton-John. So although they never met, as it turned out, Olivia Newton-John, as a teenager, refused to go to Göttingen to visit her grandfather, Nobel Prize winner Max Born. She just didn't want to make the trip. She thought it would be kind of boring to visit, this old grandfather. And now she regrets it. She recently did an interview where she said she wished she could go back in time and meet her famous grandfather who founded quantum mechanics. Now, Gamoff was considering questions like how do nuclei decay, and decided to apply quantum mechanics to that and developed this idea called quantum tunneling, that particles can tunnel through barriers, and that's how particles decay out of atomic nuclei, and that explains radioactivity. So he applied quantum mechanics to nuclear physics and founded basically modern nuclear physics. That's him with a physicist named John Cockcroft, who is a particle physicist. And this also explains how stars shine, because protons can tunnel through the same barrier and meet with each other through chance. And then the two protons get together and form heavy hydrogen. And then if another proton comes along and eventually a fourth proton, two of the protons become neutrons, and it becomes two protons and two neutrons, which is a helium nucleus. And that explains how stars shine. So under very energetic conditions, nuclear particles can quantum tunnel, unite, and they release a lot of energy in the process. And this happens in the core of stars, including the sun. Nuclear fusion. Now, Gamoff's theory also was used to show how you can collide particles such as protons with other objects, with nuclei, such as, let's say, gold foil or iron or whatever you want to collide them with in a particle collider, and produce other elements. So this enables you to transmute elements from one element to another. So you can collide protons with uranium sample, for example, and then cause fission, uranium fission. So Gamoff developed that theory. So his theory of alpha particle decay, the first theory, and then his theory of how to make colliders, each of them took about a day for him to do. He was brilliant, but he was very impatient. He did everything very quickly. So he worked on hunches. And as we'll see, both Hoyle and Gamoff always went by hunches. They were very intuitive physicists. And this is Cockcroft-Walton generator, which is used to accelerate particles. So now back to Fred Hoyle. Around this time, Hoyle went to Cambridge, and that's where he studied, and he also became a professor at Cambridge. And he took a break during World War II to work for the British military. And right after World War II, there was a mission that he needed to go on to go to the United States. And he took advantage of that to go out west and meet with an astronomer, Walter Baade. He did a tour of observatories just out of his own personal interest. And he met with Hubble, he met with Walter Baade, and he learned about, at that point, about Bade's theory that supernova are a previous population of stars in which the core collapses and the stars explode. So that was Bade's idea. Bade was the one who developed the idea of population 2 stars, population 1 stars. And now we suspect there's a population 3 stars as well. And then the population 2 stars, in their dying days, they run out of hydrogen fuel, their cores collapse, they become extremely hot, and then finally the cores collapse down to neutron stars or black holes, and then the outer envelopes of the stars explode catastrophically in supernova bursts. Now, around the same time when Hoyle returned to Cambridge, he met with 2 of his friends from the war effort. And this is Hoyle, and his friends are Herman Bondi and Thomas Gold, also known as Tommy Gold. And they went to see a movie called The Dead of Night. And The Dead of Night is a horror movie, and it sort of has a trick ending. So the film involves a man who experiences a nightmare about something terrible happening. But then he wakes up from the nightmare. He doesn't really remember it, gets a phone call inviting him to a country house. So he arrives at the country house, and when he reaches the country house, he gets there, and he tells them that he had a nightmare about the house, but he doesn't remember what happened. And then while he's at the house, everybody shares these horror stories, these horrific stories. And then eventually, I don't want to give away the end of the movie, but something terrible happens involving this person, Hugo, the ventriloquist dummy. So this is a ventriloquist played by Michael Redgrave, very excellent acting role. And the dummy gets out of hand, and not to give it away, but something horrible happens. And then the lead character wakes up in a cold sweat, and the whole thing was a nightmare, being in the house and so forth. And he's happy that it really was a nightmare, that it wasn't real. But then as he gets up, he starts to experience some amnesia. He doesn't remember what happened during the nightmare. And then he gets a phone call inviting him to a country house. And he goes to the country house, and then the same things happen again and again. So the twist ending is that he experiences this nightmare again and again in perpetuity. So it's an endless cycle. Okay. So the three astronomers go back to Bondi's apartment. They have some drinks, and over drinks, Tommy Gold says, hey, well, what if the universe is that way? What if it's always pretty much the same? It just repeats itself again and again. Now, they didn't really like the idea of cycles of expansion and contraction, because they really thought the universe just keeps expanding. But to explain how the universe can keep expanding and still look the same, they imagined that as the universe expands, even though galaxies are moving away from each other, new galaxies form over time. So galaxies are constantly being created. And they called this a steady state model of the universe. Now, Hoyle came up with a way of producing these galaxies, and that's by imagining tiny seeds of matter. So starting off as protons and neutrons, emerging into space, and then those, through gravity, clump together, form larger and larger clumps. And over billions of years, these clumps become large enough so that they can ignite in hydrogen fusion. And then they're stars. And then those stars get bigger and burn their hydrogen. And then they eventually they're going to explode and release material. And more stars form. And then the stars can clump together into galaxies, and they create the new galaxies. So in essence, the seeds of matter eventually create the galaxies that fill in the gaps formed by the expansion of the universe, the old galaxies moving away. So the difference between the Big Bang and steady state is, in the Big Bang, you imagine some kind of auditorium. So imagine, so we can use our imaginations. Imagine we're at the auditorium in the Franklin Institute, since we can't physically be in the Franklin Institute. But imagine that we're sitting there, and then suddenly somebody says, well, you really need to space out more because of restrictions. So the people in the first row have to move to the second row, but the people in the second row have to move to the fourth row. People in the fourth row have to move to the eighth row, and so forth, to allow everybody to have space. So that would be like the standard Big Bang theory. So you'd have more and more space in between. But then in the steady state theory, imagine if the auditorium was open to new people coming in, and the new people just came in, And then when people vacated rows, they rudely just sat in the rows that were vacated. And then the auditorium would still be just as packed with people because people would fill in the rows that are vacated. So it would defeat the purpose of the spacing out. The original people would space out, but then new people would fill in the seating. So the auditorium would still be just as dense with people. So that's the steady state theory. So back to the story of George Gamoff. So after he visited Göttingen, developed all these great theories, he was very famous in the Soviet Union, but the Soviet Union started to get stricter and stricter about traveling, and also started to require that people study Marxist-Leninism and incorporate that into their theories, and it became very hard for scientists to do their work. So Gamoff tried to escape. He first attempted with a rubber kayak in the Black Sea, but finally he got an invitation to the 1933 Solvay conference. At that time, he had a young wife. He got permission for her to go, and then he escaped to the West. And then he got an invitation to the United States, and he gets invited to work at George Washington University in Washington. So because he heard it was in Washington, he went to the train station, I guess Pennsylvania Station in New York, and said, I want to buy a ticket to Seattle, to the great state of Washington. Well, George Washington University is not in Washington State, it's in Washington, D.C. So he learned about his mistake and quickly got a refund and switched the ticket to Washington, D.C. So he worked at Washington, D.C., and he had a young student named Ralph Alpher, who needed a project. And Gamoff said, let's look at nuclear physics and Friedman's Big Bang idea, since Gamoff was really interested in Friedman's work, and Lemaitre's idea of the primeval atom. And let's just consider what would happen in the hot early universe, and imagine that all the elements could be created in that cauldron. So they came up with a theory, Alpher and Gamoff, in which all the elements from hydrogen all the way up to uranium could be put together in the hot early universe. So fulfilling the ancient dream of explaining where all the elements come from. Now, Gamoff loved puns, and he noticed that Alpher and his name sounded like the first and third Greek letters. And he had a friend and colleague named Hans Bethe, who was another nuclear physicist. So he added Beta's name to the paper, even though Bethe didn't do any work, just to make it a pun. Alpha, Beta, Gamma. Alpha, Beta, Gamoff, or Alpha, Beta, Gamma, the first three Greek letters. By coincidence, it was published on April 1st, 1948, April Fool's Day. So you can't really blame anyone if they didn't take the paper seriously. And to celebrate, Alpher and Gamoff took a bottle and they added a label with the word lem on it. Lem is a word that was coined by Alpher to mean the original stuff of the universe, and it actually comes from a medieval Latin word which means matter. So it's a pretty obscure word. It's not a word you hear in ordinary English, but they took this medieval Latin word, which came from ancient Greek, actually meaning matter, and they applied it to the early universe. Now, here's how they celebrated. They got a bottle of liqueur and put this sticker on it, or wrote Lem on it. And this bottle is now in the Smithsonian Institute, if you want to see it, at the Air and Space Museum. And after they proposed their theory, Alfred gave a talk about it. And their theory said that all the elements were created in the first 5 minutes. And helium itself was created in the first 3 minutes. So some of you might know a book called The First 3 Minutes, which explains how helium was created. Well, they wanted to make it so that all elements were created in the first 5 minutes. And here's a cartoon by the famous cartoonist Herblock, that a nuclear weapon was jealous because the blast of the universe happened in 5 minutes. So the atom bomb was a little bit jealous. Pretty weird, but the atom bomb was on people's mind at that point because it was 1948. But there is a problem with the theory, the alpha Gamoff theory. You build up the elements up to helium. You can put two helium elements together and make beryllium, but beryllium is extremely unstable. Beryllium-8, it decays within a trillionth of a second. So, so to make carbon, the only reasonable way to make carbon is to add more helium to beryllium, and that makes carbon-12. And then you can keep going. So there's a block or barrier in the way of making carbon. Now you need carbon to make lots of things in the universe, including you and me. People are made of lots of carbon. So people quickly realized, well, the universe is a no-go for chemical elements if you can't make carbon. And the Big Bang cools down quickly enough so that after about 2 or 3 minutes, when helium is formed, it's not quite hot enough to fuse beryllium with helium into carbon. And there's also was not really no explanation of how this could happen within a trillionth of a second. That was actually for Hoyle to come up with the real scheme. So Hoyle in 1949 goes on the BBC and goes on the BBC and disparages the Big Bang theory, not Gamoff's theory, but in general, Lemaitre's theory, because he has this better theory, which he said, steady state, the universe lasts forever, it keeps renewing itself. So Hoyle said, why have this giant explosion in the past when you can have matter continuously created very slowly? And that is, he thought, is more reasonable because you don't have this massive lack of conservation of energy. Plus, the Big Bang theory has a lot of problems, including predicting that the universe is only 3 billion years old. The original Big Bang theory said the universe is 3 billion years old. And as we know, Earth is much older than that, and the stars are much older than that. So Hoyle got a lot of popularity for the steady state theory because of his BBC programs. And the name stuck. Gamoff never liked the name Big Bang because he said the universe in the beginning was neither big and there was not a bang. It was just an expansion. Now, in general, Gamoff and Hoyle were masters at popularizing their ideas. So in the 1950s, people would be able to go to the store and pay the expensive price of 50 cents and get Gamoff's book, The Creation of the Universe, all about the Big Bang Theory, or get Hoyle's book, The Nature of the Universe, which came out around the same time, which talked about the steady state theory. And that was cheaper, 35 cents. So, so for less than $1, you can get books describing both theories of the universe in the 1950s. And it was really popular to talk about this debate.
It's interesting, Paul, that the one gentleman, Hoyle, is mostly known through kids in the modern generation today for, naming the Big Bang, actually making a joke about it. And yet, it's really George who is behind the theory. We remember Fred for all the wrong reasons, in a way. We should be celebrating his nature of the universe, his steady state theory, and instead it's the joke he makes about the creation of the universe that is the note that gives to all the students in the future.
Plus, he got around. We'll see. He got around the idea of how carbon is created. He said carbon is created when the cores of stars shrink down, and that becomes much hotter than the Big Bang, actually, than the Big Bang after 3 minutes. A massive star in which the core catastrophically collapses can produce all the elements, as we'll see. So anyway, so that was really Hoyle's major contribution. He explained how all the chemical elements formed. So both of them also wrote pop science books, science fiction, the delightful Mr. Tompkins series, which he illustrated about a bank clerk who goes into an alternate reality where the speed of light is much slower. And Hoyle wrote a lot of science fiction, dozens and dozens of famous science fiction books, The Black Cloud, the TV series A for Andromeda, about aliens coming to Earth. Gamov was a very funny cartoonist. He drew lots of cartoons. This is Niels Bohr as Mickey Mouse. So there's a whole series like that. So the steady state theory kept its popularity because the Big Bang theory originally said that the universe was younger than its stars. And there was even a debate among famous people. Pope Pius endorsed the Big Bang theory and gave a speech how it was an emblem of God's creation. But the British astronomer Royal endorsed the steady state theory, the most famous astronomer in the UK. So, so in the meantime, Hoyle came up with this brilliant idea, which I talk about in the book, of how the chemical elements are really made, and that's through collapsing stars. So we now know that all the chemical elements, except for helium, are made in the stars. So much helium is made in the universe that it has to be made in the Big Bang. We can't account for all the helium through stars. So Gamov was partly right about how the elements are created. He showed how all the elements up to helium are created. So hydrogen and helium. Hoyle, along with three other astronomers, Margaret Burbidge, Jeff Burbidge, and Willie Fowler, proved the idea that all the elements, chemical elements, are created in stars and released during supernova explosions. And Fowler won the Nobel Prize for that. And a lot of people think that Hoyle should have won the Nobel Prize, but there's a whole controversy about that. So I don't want to give too much away because there's a lot more stuff in my book. So, in fact, my wife, who occasionally attends my talks, her big advice during a talk for a previous book was, don't give too much away during the talk. We want people to buy the book. And as a result, I'm not going to explain how the battle between the Big Bang and steady state was resolved. I'm not going to say why Hoyle didn't win the Nobel Prize or talk about what happened to the two of them in their later years. There's a lot more stuff in my book, and I'll just leave this image as a hint. This is an instrument that was used to help resolve the Big Bang versus steady state dilemma through an accidental discovery of a radio hiss.
And I just wanted to mention that Lou did put a link to the website for your book in the chat. So if anyone wants to go ahead and look at it closer, the link is there.
Thanks,
okay,
Lou.
I didn't have a chance to look at the chat.
Oh, I had well, it's a good time to jump in with a question or two. I had one question that you might
Okay,
know,
so I'm gonna stop here and then
okay.
questions. I hope this is the right amount of time for the talk.
Yeah, no, this is perfect, Paul. No, thank you very much.
Great.
I had a question myself. I was wondering, do you ever know if Edwin Hubble publicly credited Henrietta Lovett for some of the work that, he's building on her shoulders?
Well, Hubble was notorious for being rather snooty, and I don't believe he credited significant. I'm almost positive. I can say an answer to that question. I'm almost positive he didn't credit her, because she wasn't even, from the point of view of the astronomical community at that time, she wasn't even a real astronomer. She was considered like practically a clerk. And that's very sad. It shows you the role of women in astronomy at the time, and the role of people who did calculations, computations. So she worked at Harvard Observatory, which is now Harvard-Smithsonian Observatory, and she took down a lot of data about these Cepheid variable stars. And then another person who contributed was Vesta Slipher, who came up with all this Doppler shift data, essentially, proving that that what were called the nebulae were really moving way too quickly to be in the Milky Way. So he could have guessed from his paper that Andromeda and other so-called nebulae were really galaxies in their own right. And Henrietta Leavitt could have guessed that some of these Cepheids were beyond the Milky Way from their distance measurements. But she didn't really continue with her work. She just gave it to the Harvard Observatory and moved on to other projects.
Still, your answer kind of it validates me. I've taught about Edwin Hubble for years. We always had to talk about, astronomy, history of astronomy in school. And I'd said to many generations of kids, it's a shame that people didn't credit women properly for what they brought to the field. Yeah. And I used to say to children, I think that Henrietta Leavitt was overlooked, for some of her contributions. And we bumped into this in other talks with another woman, Carolyn Herschel, another woman in astronomy, the first professional astronomer. Uh-huh. And again, it was this idea that men had. I think that they just thought that women didn't have the capability, to really bring that forward.
Oh God, I have I'm not going to show it, but I found a cartoon. In fact, I went to the Herschel house when I was doing research of the book. I went down to Southern England to Bath. And I always wanted to see the Herschel Museum. I was down there for another reason, to visit a friend, but I went to the Herschel Museum, and they had up on the wall a cartoon of Carolyn Herschel, and they even in her time they made fun of her. They said isn't it silly that there's a woman astronomer? Like, how could she possibly detect comets and so forth? And it was kind of a crude cartoon. I really found it I'm sure everybody found it very objectionable. But Hoyle, to his credit, was always calling attention to the underdogs. He considered himself kind of an underdog because he was from Northern England, from a small town. Right. And he was the one who really emphasized that Jocelyn Bell Burnell should have gotten the Nobel Prize for discovery of pulsars. And he gave talks on radio stations and said the Nobel Prize was given to the wrong person. And he got in trouble for that because Anthony Hewish was his colleague and got really mad and said, look, it wasn't my fault that she didn't get the Nobel Prize. I gave her credit on all the papers. And Hoyle had to apologize for that. But it's possible that the Nobel Committee was upset, and that could be one of the reasons why Hoyle himself didn't get a Nobel Prize. And Hoyle said we should give more credit to Vestas Slipher for his work that was essentially Hubble's results, but just didn't say that the universe is expanding, but strongly suggested that the universe is expanding.
It's a shame because I feel like the major contributions that women have brought forward over time in astronomy, it's just we've short-circuited ourselves in a way. I sometimes wonder if it's that male ego that just gets in the way, thinking that we have a superior, grasp. And it really just comes through time and again when I hear what you talk about, when I hear about history, and we've overlooked the women definitely. Yeah. So I'm glad I'm in a society that doesn't do that. We feature more women, and we try to, because we really think that that's a major contribution that we've overlooked. Oh, and one other quick question I had, and we want to do a couple shorties here if you want to hold for questions at the end, but I was thinking you talked about population 1, 2, and 3 stars. Are you referring to something, is that the same as when I call first generation stars versus later generation stars?
Yeah, I mean, people
am I close or
call them stellar generations. So the technical term, I think this was coined by Walter Body himself. He said that population 1 stars are stars like the sun.
Okay.
And these are stars that were developed after heavy elements were created in the universe. So they have some heavy elements in their core. And then of course they have, some of them have planetary systems with heavy elements. Mm-hmm. And then population 2 stars, it's confusing because population 2 are the previous generation. And then population 2 are the ones that start out mostly as or completely as hydrogen, and then burn that to helium in their cores, and then have the catastrophic explosions that
Okay.
produce
The heavy elements.
what astronomers call metals.
Right.
I don't know if you're familiar with the term metal, meaning everything heavier than helium.
Okay. Right. Okay.
So it's funny, yeah. So physicists would call iron a metal, but they wouldn't call carbon a metal. But many astronomers will call anything beyond helium a metal.
So what does population 3 stars then take us to?
That's hypothetical. They would be stars that are extraordinarily massive, made purely of hydrogen. They would be the first stars in the early universe.
Okay.
There's a theory, I believe, that when they catastrophically exploded, they would only exist for a short period of time.
Yeah.
They would produce a supermassive black hole in their core, or a mass, not necessarily the supermassive black holes we see in galaxies, but a giant black hole, and that giant black hole over time would coalesce with other giant black holes and form the supermassive black holes. And then those supermassive black holes would form a huge cluster of matter, extremely massive, as massive as a million stars, a million suns.
Mm-hmm.
And that would form the seed for a galaxy to form around it.
Wow. Okay. Gotcha.
So that's one theory of how galaxies formed.
Right. Okay. No, it's interesting how the population 1, 2, and 3 kind of weaves through all these ideas that I've heard. I just haven't. Okay. No, it makes sense to me now.
But the population 3 stars would be before
the earliest,
before galaxies.
Yeah. Right. Before galaxies. Population 2 would be what I've been referring to as first generational stars that explode and make the heavier. Okay. Oh, all right. Cool. That makes sense. I'm
teaching a course on the physics of stars, so I have to use terminology. Yeah.
Okay. Do you do it online?
I'm actually last year and this year teaching all my main courses in person. So even last year I taught, and this year I'm teaching with a mask on.
Okay.
So I like teaching in person, but luckily I was allowed to do it, and I'm still allowed to do it because it's small groups. Now everybody's vaccinated, or almost everybody's vaccinated, and we're all wearing masks. So
but I feel your distress, because a good teacher really does accommodate the audience while they talk.
Yeah.
And I know
Looks like Ted froze.
Oh, okay. I was that was me or him.
We have another question. Al would like to know, how has dark matter and dark energy changed the theories taught us in school? And then he put a long time ago.
Well, so dark matter was discovered in part by someone named Vera Rubin, speaking about pioneering women astronomers. And she worked with somebody named Kent Ford at Carnegie Institution. And her thesis advisor was George Gamoff. So there's a connection with Gamov there. Gamov inspired her. And she found that stars in the periphery of galaxies move much faster than they should based on the visible material, and speculated that there was missing material, and that's what we call dark matter. So we don't know what dark matter is, so we don't know how dark matter is created. So I can't really say, oh yes, dark matter is created in stars, because we have no idea where dark matter is created. It probably was created in the early universe somehow, but we don't know what it is. And it could be just a problem with gravitational theory, which is the other hypothesis. And then dark energy, it acts a little bit like Einstein's original cosmological constant, acting as kind of an anti-gravity term, and it makes the galaxies move faster and faster away from each other. And in Hoyle's last paper, he died 20 years ago in 2001. He tried to explain, using a modified version of the steady-state theory, how dark energy works. So he kept going. He never except very briefly, never really believed in the Big Bang. He kept trying to come up with alternatives.
A question from our members. Would long-lived brown dwarfs be population 2 or population 3 stars? It's kind of like a low ball throwing that into you, because brown dwarfs, especially a lot of them we've only recently discovered around here.
Brown dwarfs would be, brown dwarf basically is hydrogen that's not massive enough to ignite.
Right.
So I would call it population 2.
Okay.
But
thank you. Good question.
Yeah.
And I don't know if we want to do more questions, but Denise, since I'm back, how about we throw it over to you for a bit? Dr. Halpern, thank you very much. If you can hang around for a bit, it'd be great. If you can't, I totally get that. Denise does a short planet report and Dave does a short rocket science report.
Well, let me know how long I would have to hang out, because
well, we'll have Denise on for 10 minutes and I have Dave on for
I don't know
10
if I'll be 10 minutes.
Okay. Do you want to do
okay,
let's
I'll
say-
hang out then.
Yeah, I might be
Eventually
shorter
have
than
to
that too. I'm just going to
train
blast
them.
through.
Yeah.
Okay, so it'll be short.
Okay,
because
that's fine.
we
I'll
were
hang
enjoy-
out then.
We were enjoying you, so we kind of let
Thank
it
you.
go.
Great.
Okay. Okay, so Denise, you want to share your screen and take over there?
All
Denise
righty,
is our
I
vice
do.
president. She
Hi,
does a-
everybody.
She has a normal.
Paul, I
feature with
enjoyed
us.
your talk. I always think of when you were talking about what was it, the seeds of matter and the life cycle stars. It always reminds me of the Lion King. You know,
Oh,
when they
really?
break out into song, the circle of life, you know, the circle of
wish
stars.
I wish I could sing, but
Yeah, just
at this point, my wife would say, like, please don't sing.
all right, let me see if I can get rid of that. Well, first, I want to show you my desktop because I just really love these pictures from Juno spacecraft. And since Jupiter's in the sky right now, it's just amazing. I absolutely enjoy. I would hang these on all over my house. These pictures of Jupiter that are coming out. I don't know if you can see, but there's like little bumps. It looks like braille down here. Like, what are they? And it's just so exciting and so beautiful. So thought I'd show you that while I had to start. Since my desktop was there. The other thing I wanted to show you, first thing I saw this morning when I got up was this, storm watch aurora sighting. Not for us, obviously, we're a little too low, but at the poles, the coronal mass ejection that just happened a day or two ago. And I read it can take like between 15 hours and a couple of days for these particles to actually hit the earth and cause the aurora. So that's heading at us now. And you can see the video of it and learn more about it on spaceweather.com. So I'm going to quit Safari because it's probably using my internet. And I'm just going to open up Sky Safari, plain and simple. So right now, if you went outside and it was clear rather than a torrential downpour with tornado warnings, Venus, Saturn, and Jupiter are all the visible naked eye planets. If you're up a little bit, if you're out a little bit earlier and you have a really good view of the horizon, maybe with binoculars, you might be able to spot Mercury. Probably somebody like Joe has already seen it. And the moon is up kind of in the morning now because we're in that waning phase headed towards new moon next month. So I left the zodiac up, and I guess I can make this a little bit bigger. But I wanted to go through a couple of days and just show you how that moon is actually going to come through through the course, and we can actually see how things go through the ecliptic. So I have this set on days, and hopefully I do this properly and not make anybody sick. Now, I knew I was going to do that. So if we can watch, you can see the moon moving through the ecliptic down there. Actually, it's gone now because it's a new moon. And I actually don't think this is working properly. So I don't want to do it too fast.
I see it.
Yeah, it is. It is going. It's just because we're going a day in advance. It's a little bit harder to understand. But so all these planets move through the ecliptic, as we know. That's why they're called planets. People notice that there are these wandering stars through certain constellations, and that's where you want to look. So the best way to find that, as we know, is looking towards south, southeast, southwest. That's where Venus is going to be in the west southwest. And Saturn and Jupiter are almost right at southeast, and they get to be their best exposure around 10 o'clock. So if you want to look at them through telescope, Ted, I'm curious how your imaging came out of Jupiter the other night. Did they look like Juno or the Juno images, or
No,
did you get the
Juno
transits
images,
and stuff?
But considering from Philadelphia with what we've got over top of us, excellent images. I can actually pick out quite a lot of detail.
Hopefully,
I don't know if I can share it that quick tonight, but I might do it at an Astrocora too.
Okay.
Didn't think about it, but yes, had some. Just so you all know, I'm practicing for Wyoming because we'll be doing Jupiter and Saturn, featuring it each night. And Denise has been listening to me try to learn how to do this through video.
Oh, that's okay. I enjoy it. So Venus is still up right now. So, next couple of days, you can go out once it's finally clear. Keep checking out Venus. We have plenty of time for that. And Saturn and Jupiter are the ones. Now, if you have a nice telescope, you might want to look for Pluto. Apparently, Joe has seen it, which I think is amazing. Maybe Joe will have to let us know what size telescope is needed to actually see Pluto. And was it worth it? And Neptune, which I've seen in a small telescope. And if we stay up a little bit later, sorry about that. For some reason, the program is not being fun tonight. But anyway, if you go towards the morning hours, you should be able to see Uranus. And if you are up in the morning, don't forget that Winter Circle is giving us a preview. Yay, I can't wait, of the winter skies and just the cooler weather, which I'm excited about. Right now is a great time to look for the Great Square of Pegasus. And there are a couple of supernovas out there that we were talking about. I'm going to go backwards. Let's see if I can do this easily without making anybody sick. Incidentally, I just started work as well live. For the summer, I was live, and it's just so much better being in. I mean, I love doing this on the computer, but nothing beats the excitement of a live audience, especially with kids, because they're just so excited about it. So yeah. Anyway, there we got Uranus in the morning up around Aries, but there's some other stuff up there that I just wanted to mention real quick. Let's just get rid of these and show all the constellations. Here in Ophiuchus, the quote unquote 13th member of the zodiac, because planets do sometimes go around his legs. But I do believe right around here is where that supernova is.
Not a supernova.
Not as RS
Ophiuchi.
Yes, excuse me. I was thinking of the one in Cassiopeia. That's all. You need telescopes for both of them at this point right now.
Binoculars will do.
Binoculars will do. Okay. Yeah, they're about both around 8th magnitude. I just
More or
read.
less. Not sure about Cassiopeia, which is a regular old nova, and that one's been bouncing around all over the place. It just refuses to die. It may be brighter than 8 now. I haven't looked.
Well, let's check out where that one is. That one, if we look here at Cassiopeia, that one is up around a Messier number.
M52.
M52, yes. So if we go in, which should be up around here, there it is, M52, which is a nice little open cluster that you can look at as well. Let's see if we can get a picture of it. I'm on M52. This program is just giving me a hard time tonight. Yay. But that's okay. Things happen. It doesn't matter. It's an open cluster you can see, and it's right near that. It can help you find that. It's right near there, very close to it. Other things, we got the summer triangle. It's a great time to look for the Milky Way. So if you're into galaxies, we can look at our galaxy, and we can look at the Andromeda galaxy. I always find it you can either go between Cassiopeia and Alpheus, the side, the end corner of the square, and it's right in between the two. Or if you have a good view and you can see Andromeda, 1 star, 2 stars, and right up a little bit, like a couple of degrees up, and you find it easy peasy every time you stick your binoculars there. So Mars kind of in the glare of the sun. Mercury can be seen if you have a really good view of the horizon. Jupiter and Saturn are going to be the kings and queens of fall. I guess they were both kings in their own right. And we need more. Well, Venus is a woman planet. But anyway, I'm getting ahead of myself because this software messed me up tonight. So I'm going to leave it at that. We do have a couple of planets. That's exciting. Always fun to look at Jupiter and Saturn, and, Uranus, Neptune, okay. And Venus, just, I enjoy looking at that without any optical aid. It's just so pretty. And it's nice to see it in our evening sky. So that's it for me.
I found it, Venus. I found it. Can I close out your talk? You ready?
Yeah.
I'm going to try this one.
I'll stop sharing.
You said, how'd that go the other night, Ted? So I'm brave enough. Can you guys see it now?
Well, it had to go better than my talk tonight. So there you go.
What do you think? This is Jupiter from the backyard.
Oh, wow. You can see the red spot and everything.
Yeah. So what I'm doing here for this one, it was a live video image. And what I do is I stack about 20 of them live on top of each other. And they're only about 25 to 30-second exposures. So you're basically getting like a live feed. And what Denise was asking about is, this is what I'm hoping to preview out in Wyoming. And I hope I get a little bit even clearer, but I'm getting there. I'm doing pretty good with this one. Okay, I'll stop sharing that one. But you asked Denise, so I thought I'd share.
No, that's great.
Yeah,
No, I'm jealous. I want to start doing photography.
Denise,
Yes.
you had mentioned Pluto, and I have a picture if you want to see it, that Larry and our intern Ian, I think Ian's on tonight.
He was.
They
Let's see him
took
now.
a series of images of Pluto and
Oh, cool.
post them just to see how it moves across the sky.
I think I have you as I can share. Can you share the screen now real quick? Let me make sure.
No, he's not.
No, where's he at? Ryan Observatory. If anyone sees him, go ahead and make him share.
I'm not allowed
I got
to.
it. I
Reason.
got it more. And go ahead. You're a co-host, Al.
It says, okay, there I am. Okay.
So this is from the observatory now. Oh boy. Look
Yeah,
at this.
it is. And I don't know if you can see it, but
Yeah, the
Yeah.
arrows. Yeah.
the first night was the 24th. The second night, the 25th, it moved to here, and the 26th it moved to there.
Wow.
Against the background.
Yeah, that's pretty cool.
That's good. That's excellent. Ian took this?
Yeah, Ian and Larry together.
Well, good job, Ian. If this is your first shot, you're already ahead of me.
Who made the composite with the Pluto text with the picture of it behind there? That's a good idea.
Larry did that.
Okay,
Oh,
that's a good idea.
Larry, if you're
too.
on here also, good job on that.
That's fun.
Hey, let's
Moved a lot.
show this again. Let's show this again at the Muddy Run live stream.
It moved more than I thought it would.
Yeah, it moved more than I thought. So also,
Yeah, apparently
What
it's
the image scale is,
right? Yeah, okay.
you magnify the heck out of it, of course it's going to move a lot. And conversely, if you don't magnify it, it's not going to look like it moved a lot.
Okay. Okay.
But I've seen
Cool.
that visually. I mean, that's still me. The neatest thing is to see it with your own eye.
Well, let's stay on time here so I can keep Dr. Halpern with us. I want to switch over to Dave Walker. Dave, you want to do a little rocket science with us, and it'll finish out our meeting tonight?
Oh, yeah.
Event.
Event.
Yes.
Well, welcome all of my space cadets out there. It's actually, I was thinking the other day, it's been a long, long time since I've actually done a piece on the actual technology, because just keeping up with news is keeping me busy enough. So let me just share my screen, and we'll go over the latest news since August. And there's always so much. As I always say, it is often the hardest part is selecting what not to include, because it's also great out there. There's several really great websites, and I really encourage people to go out there and check. So
Dave,
let's get
is
going.
your camera off purposely? Oh, here we go. You're sharing
I've got a
session.
really bad I've got
Okay.
a really bad network connection, so
We're seeing your first slide.
no, we're not seeing my first slide. Something, and there we go. I'm having a lot of tech problems today. I'm on my secondary computer, and my network is down. but I'll give you the whole news.
Go ahead.
Speaking of planets following along, if you've been following the Bepi-Colombo mission, which is eventually headed to Mercury, it just did a double swing by Venus and took some more information about it, including its gravity, temperature, magnetic field, and winds. So this is a good high-resolution heat-shielded device that's teaching us more about what could have been Earth's twin until the runaway greenhouse effect took part. Coming a little closer to home, China has completed the second EVA on its third space station and its first modular space station, Tianhe. Mission commander Ni Haxiang and first operator Liu Boming installed cameras and some cooling equipment on the outside of this modular space station. Tianwen space station, Tianzheng space stations were just one-offs and they burned up in re-entry. But this is their first modular, so they're joining the club that the Soviet Union started with Mir. We're doing with a bunch of partners with International Space Station, and they're doing this, including with some European partners. So welcome to the club. There's lots going on up there. Speaking of things going up, one of the things that is not is the Space Launch System. It has been undergoing stacking and testing. Here we see it inside the Vehicle Assembly Building down at Kennedy Space Center. But between slowdowns due to the resurgence of the COVID virus and really poor weather, plus a few unexpected technical problems, they might not get to launch it until spring of 2022. They're still aiming for some time before the end of 2021, but it's not looking good for this giant rocket. Speaking of rockets, the latest bit has been added to the space station. This is the Nauka module. It is virtually the same as the Zarya functional cargo block that was the very first part of the space station, launched from Russia in 1998, and this is the first major module added in 20 years. They've added some smaller modules, but this is the first biggie. It has propulsion, solar power, and a whole bunch of docking ports to add capability for both Soyuz crew capsules, Progress equipment capsules, and European-style capsules. It's replacing the old Piers module, and we just lost my connection there, so we'll just get it right back, which was jettisoned and burned up in Earth's atmosphere. It did do something kind of funny. Right after they docked it on the 29th of August, they had some problems getting it to dock properly. We're not sure whether it was mechanical or human error, fired its thrusters continuously, sending the space station for 1.5 loops around its axis until it finally ran out of fuel. So that must have been amusing. So they've got it under control, but the problems with the space station don't stop there. In 2009, they discovered cracks in the old Zvezda module, and now they've found more cracks and a slight leak. So, you know, we're talking about 22-year-old hardware, 23-year-old hardware here. It's getting to the end of life, and there's might not be a graceful way to take it apart and replace bits. So I'm sure there are a lot of engineers, both at Roscosmos and the NASA and ESA, that are kind of sweating the details on this one. A little closer to home and for a little bit of fun, Estes Model Rockets has issued a limited edition of the Blue Shepard that flew last month, taking 6 passengers to the edge of space and back. It comes in 2 sets. One is just the rocket. One also includes launch packs and engines. The single unit is $69. I've already got mine on pre-order. It's a 1/66 scale model, and on its biggest engine, it can fly to 133 meters. And it can carry tiny payloads in the little Blue Origin capsule. So I thought that was pretty cool. I'm going to add that to my Saturn. We've got a couple other model rockets. The big transparent fins at the bottom are not on the real rocket. They're just necessary because, well, you know, models.
Models.
Speaking of, yes, just look it up. The jokes write themselves. Speaking of jokes writing themselves, micro rockets to carry CubeSats and stuff into space at low cost are becoming a big industry for people that don't want to wait for ride sharing on the bigger rockets like the Falcon and the Atlas and the Vulcan and the Delta and the So one of them launches from Alaska. It does polar orbits, and they had a little problem on launch. Rocket Lab's Astro rocket lost an engine shortly after ignition. Whoop, come on, let's go. I've been having video problems with my machine. So here we see it taking off over that beautiful Alaska landscape. There goes the engine, and it just kind of scoots sideways right out of a gate in a chain link fence that someone conveniently left open. Otherwise, it probably would have tipped over. It started to ascend as it lost mass from burning propellant, but it failed to reach orbit. But, you know, if you know me, what's one of my rocket science tales without a good launch, good explosion, or good failure? And with that, I am going to say good night. This is Dave Walker signing off for the Rittenhouse Astronomical Society, just letting you know what's up.
Thank you, Dave. Hey, if you've just tuned in from our YouTube site, you've been watching our fall event, a September event from the Rittenhouse Astronomical Society with Dr. Paul Halpern. You also had a little bit of a treat there with Denise with her planet report and Dave Walker with rocket science. So it brings us kind of to the end of our meeting. And I do have another question for Paul since he hung out there with us for a bit. I have a kind of a question here. Let me see if I can phrase this right. It came in from the audience. Where is it? I think it was coming in from Al. What he wanted to know is when when dark energy and dark matter become discovered, are they encompassed into earlier theories that we've been taught by these gentlemen, or does it change the theories? What effect does it have on them?
Well, it depends on what dark matter is.
Okay. Because we only infer it, right?
Yeah,
we infer its existence.
It could really change things if it turned out to be a new form of matter or reflect a new force. Okay. And dark energy, the dynamics of it were ironically predicted by Einstein in his cosmological constant.
Right.
So I'm sure the discovery of either one, the confirmation that there are certain substance, would really revolutionize science. But it's hard to say since we don't know what either of them are.
Right. Okay. So good answer. I'll say that. Anybody else out there in the audience? And by the way, I'm going to sign off on the YouTube channel right now. I want to make sure I can do that